here we're taking this thing. So 0 cross 0 till 0 cross, so yeah, 0 cross any number. Let's just take half. This is an example of an open set since it's the order topology with a least element. We have an open set that's not intersecting the set A at all, right? So this is the only set we really had to worry about. So yeah. Now for the B set, we really only have to worry. So in a similar argument, we take any point that's not included anywhere else. We don't have to worry about anything, right? Yeah. Now, oh, we might have to worry about that. Let's see. So comma zero or 1 cross 0 might be a point we have to worry about. So let's say we take any neighborhood around it. It's going to have to be from some point or the other, right? And from that point, yeah. Yeah, so 1 comma 0 is a problem. 1 cross 0, yeah. Yeah. Because whatever point you take, there's going to be a 1 minus 1 by n cross half in between there. Yeah. So it's quite weird, right? You think that 1 cross half would be the point limit point, but that's not the case at all. We can just find a neighborhood here and it's not intersecting anything. It's this point that's the problem. So any other point? Oh, it might be worse. Let's see. No, actually, if it's any other point, then it's going to be between two 1 by n essentially. So we can just make sure it stays between those two 1 by n. Yeah, that's fine. Yeah. Okay, I'll be honest. I did not think of this before recording. So if I went through with the solution I thought of, I would have screwed this up too. So this is quite a question you have to be careful about. You have to consider every point and then you have to consider some neighborhood around it. So you have to actually manually check every single point. And note that the open sets here are, A cross B, comma C cross D, right? So yeah, note that. Okay. Yeah. So for C, do we have to worry about it? Let's see. So do we truly not have to worry about it? So here, oh wow. Yeah, the top might be a problem. I did not think about the top at all. Wow. Okay. Uh, wow. Now that I have to worry about the top in question C, I'll check question A too now. Uh, what about this one? Yeah, let's think about 1 comma 0. Yep, that's sad, but A has 1 comma 0 as a limit point. Wow. Okay. So we have to worry about the top and the bottom, and yeah, any point in between is fine because if it's not intersecting anywhere, we can just go near it. So it's fine. Yeah. You know what? I'm going to spend a full 5-10 minutes on it and then what happens. So yeah. Okay, so there's bad news and good news. The bad news is the ordered square was a lot scarier than I thought it was. It's you have to there's a whole pathology from here and here. Like the top and the bottom create a whole new system that you just have to yeah study and it will bother you. That's the bad news. The good news is it's only the top and bottom that are going to bother you. Everything else is fine. So if it's an interior point, essentially you can always find a small enough interval that's containing it. If it's the edge, you always have this and this, right? So even here we're fine. And if it's another point, again we can find an interior. It's fine. It's the top and the bottom, except for the last point at the this point. Yeah, but any point you take here, any neighborhood that you have here, you have to go back, and it has to go back to some point here. And the problem with some point there and not, it's not an immediate predecessor, right? That's the whole problem. If it was an immediate predecessor, we would be completely fine. But because it's not, you have to start here somewhere. Doesn't matter where, somewhere, and you go down, 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 and then you come here. So you're crossing a whole wide array of points here, continuum many points. You just have to cross some square rectangular interval to get any open set at the bottom. And the same thing for the top. And that's the pathology, not topology, of the ordered square. But yeah, I think that covers everything though. There's nothing more to unlock. But that is precisely why this question was designed, and exactly what I screwed up. I screwed up big time when I attempted it for the first time. This was something I only realized. But yes, at least I realized it. Oh well. So besides, so the anything that's not obvious is going to lie in the top and bottom. Everything else, your intuition will pretty much be correct. So let's start all over. So the square is retained. I'll just erase some of it. Yeah, yeah. Okay, ordered square. Yeah. So for the first one, we have what points to both? So we have half. We have one as well. Oh, we have one as well. That's a bit of a problem. Okay. We have one half, one third, one quarter, so on until zero. Okay. So yeah, is the top a problem? Right? Zero is not a problem. We can just get a closed interval. So it can, thankfully, because zero is the least element, we can have an open interval of this form. So we have no problem here. Right? Yeah. But for the top, we might have a problem. So any open interval here, we go to any point, let's say any point here, it has to cross infinitely many times, right? Just has to go over a whole rectangle to finally reach here, right? So it has to cross everything here, and that means it has to cross at least infinitely many 1/n, right? You cannot avoid that. So any open neighborhood surrounding one, you're going to have to cross 1/n. Now anything else, we can avoid them thankfully. So let's say we have a number that's greater than zero. So 1 comma c, let's say, yeah, hang on, I'll write it properly. 1 cross c, yeah. So this c, by the Archimedean property, since it's not zero, is going to lie between some 1/n and 1/n plus 1, right? And the good news is we can take such a, so we find what, a c plus epsilon, just find some real number. You can do that. There's no problem because of density. So you find some real number that's between c and n plus 1, 1/n plus 1. And yeah, the point is you go from some open interval to c, and then you go till the c and c plus 1 by epsilon, c plus epsilon, and you completely avoid these 2 points. It's in between, right? And you can do it for every real number after 0. So the only limit point, thankfully, is 1 comma 0, but yes, that is an additional limit point. And yeah, the that's the first one. And there are far worse examples. So yeah, we this just got 5 times harder. Oh well. Yeah. So only 1 0 is there. Also for any bottom point, the same argument holds. So yeah, you can just avoid the infinitely many. You can avoid at least these squares by going choosing two real numbers between these, right? So one, the original one, and the other one that's allowing you to have a rectangle that's small enough to. So yeah, you just have 2 points here, and then you need a rectangle that's small enough to be contained between the 2 points, two fractions. So yeah, quite bad. B, let's see. So yeah, so we have 1 minus So we have 0 here. Okay. We have half, we have 1/3, 1/4, and then all the way to 1. Yeah. So now, because it's not the top and bottom, surprisingly, 1 comma half is not a limit point. We just have this, and that's completely fine. But the bottom here, this one, what is it? 1 comma 0. Hang on, sorry. Oh, this was 0 comma 1, wasn't it? So this was, no, this was 1 comma, hang on. Yeah, this was 0 comma 1, yes, but this was C comma 1, not, yeah. You get the idea though. I'm already flipping everything around. Oh, well. Yeah, 0 comma 1, 1 comma 0 will be a limit point because you take any real number, it's going to intersect this infinite tail here. So you can't avoid it. Any other thing you can avoid, same argument, same argument. Yeah. Now, anything else? So you just need to check for the top and bottom, and the rest is intuitively true. So any point here, it's fine, it's fine, it's fine, it's fine, it's all fine, it's fine, fine. At the top and bottom, you can find this rectangle, so it's fine. Same thing here. Okay, yeah, let's just check for the bottoms at each natural number. Just check. Yeah, it's fine. So you have anything here, you can go behind, and if you have anything here, you can find a thin enough rectangle. If you have anything at the bottom, you can also just avoid it. So you're fine. Yeah, and that holds for all the things at the bottom. So 1 comma 0 is the only thing to do. Yeah, but yes, you have to check all points. You can be surprised. And with C, you will be surprised. Yes, C was the most surprising one. So it's essentially all points except 0 comma 0 and 1 comma 0, and it's x comma 0, right? Yeah. Okay, so this entire bottom line. And the thing is, this entire top line is included in the set of limit points except for 1 comma 1. So 1 comma 1 is not touching it in the slightest because of this one, right? So 1 comma 1 is safe. 0 comma 1 is not safe because any neighborhood you take is going to have a rectangle and it's going to intersect all of them. And in fact, the entirety of, so let's see, how do I write it down? X comma 1, x belonging to 0 comma 1. This entire set is part of the limit points, right? Everything else we're fine because of this example, but yeah. And what about 0 comma 0? That's surprisingly also safe, right? 1 comma 0 is. So what, to summarize, we have x comma 0. Yeah, we have this set and this set. So we have all in the bottom except for 0 comma 0, all in the top except for 1 comma 1. And everything is else is yeah. Thankfully, everything else is fine. So if we have anything here, we're fine. Yeah, it's all fine. But the top and bottom will, yeah, they'll. This is traumatizing, honestly. Now, what about x plus 2? I think we have a similar problem here. So, yeah. So even here in x plus 2, where we're having everything, we have everything here except for the endpoints. Yeah. So 1 comma 0 here will intersect them all. So it's a limit point. 0 comma 0 is fine. 1 comma 1 is fine. This is not fine. So we still have these two added to the set of limit points. And let's check about these. So these two, this is fine. We have this part, and this is also fine. We have, yeah. So it's these two new, these two are the limit points to worry about, and these two are included here too, and the original set, and nothing. Yeah, quite bad. So the reason this part at half is safe is because, yeah, we're completely fine here. I hope you get these diagrams. Essentially, I'm drawing open sets from open intervals. So, you know, you have to be careful what these intervals are. And essentially, the whole point is You have to select some number, and between any two numbers there are infinitely many numbers, continue of many numbers, and that's the whole problem of the exercise. Yeah, that solves D part. And for E part is also surprisingly safe. Yeah, so in E part we have this way, and because it's a ray and not this way, it's only including this point. So this point is included, and so is this point, but any other point we're safe. Yeah. So essentially it becomes y between 0 and 1, and both are included. That's the close set. But yeah, this was traumatizing. And yeah, you should really play around with it and understand what I really mean by the good news and bad news. The whole going backwards and covering a whole rectangle. And yeah, but I do think there is nothing more to look out for. But yeah, that is the pathology of the ordered square. I think that's what the title should be. Yeah, the title would be too long if I included it, so probably not. Okay, boundary. So boundary is defined as A closure intersection X minus A closure. So essentially, any neighborhood in boundary of A has to intersect both A and its complement. That's another way of defining it. Okay. So let's see. Let X belong to yeah. Let X not belong to boundary of A, right? Um, no, that won't work. Hang on. Yeah, so I worked it out. Let's just explain it now. Okay. Yeah. So let's assume that X belongs to the interior of A, right? Now, if I so observe this. If I show that this implies X does not belong to the boundary of A, that will mean that X belonging to the interior of A and the boundary of A simultaneously cannot happen. And that precisely means that their intersection is 0, right? Or 5. So yeah, let's go with this. Now, interior of A is a subset of A, right? So, and this is open, right? So there exists a neighborhood of X such that U intersection X minus A. Now note that A intersection X minus A is 5, so U intersection X minus A is also 5. And this implies that X does not belong to limit of A, right? Yeah. Sorry, limit of X minus A. And this means that, well, X does not belong to boundary of A. And so we're done. They're disjoint. Now, if X belongs to a closure, there are two cases. X belongs to A or X doesn't belong, right? Now, if X belongs to A, it has to belong to interior of A, right? So we are in this case we are done, and so we're trying to show that A is currently a subset of A closure, a subset of interior of A union boundary, right? Then we'll show the other case. The other case is actually quite trivial since this is a subset of A and therefore a subset of A closure, and this is also a subset of A closure through this, right? A closure, the intersection, anything is going to be a subset of A closure. So this one is actually trivial. Now for this one, if X is not in A, well, what does that mean? That means X has to belong to X minus A, correct? But this implies it belongs to X minus A closure since it's a subset. So it belongs to this and this, which implies X belongs to boundary of A. So we're done. It belongs to either of the others. right? So we have two cases and both of them lead to the opposite. So yeah, I mean, this actually could lie in if X belongs to A. Yeah, maybe not. I'm not sure. Oh, wait, something might be wrong. Let's see. So yeah, this was completely wrong. So yeah, X belongs to A. If X doesn't belong to A, I guess it's fine. Yeah, yeah, this line of thought is completely fine. Hmm. Right. Let's see. Okay, so I'm slightly changing it. It's a bit wrong, or at least not as clean. I'm not sure. Yeah, I'm just rewriting it. So X belongs. Yeah. So we're proving the non-trivial inclusion now. So now we have two cases. X does not belong to X minus A closure, and X does not belong to X minus A closure. And here we just have X belongs to the boundary of A. So we're done. And for this one, now let's see. Yeah. Hmm. So X minus X minus A closure is an open set, right? And this open set is, yeah, so how do you show it's an open set that contains, that is contained in it, right? Oh yeah, that's actually pretty easy. So this is going to be, so this contains X minus A, right? And therefore, can we show that this is contained in A? It's, yeah, I think it works out, right? Since X minus X minus A is A, so we're just containing it and reversing it, right? I think you can prove it that theoretically. So yeah, yeah. So this works out because of this containment, and then you're just flipping it. So this is the complement, this is the complement, and the inclusions reverse. Yeah, I think it works out. You can write a proof of it using the contrapositive logic. Yeah. So from that, what do we get? We get an open set that's contained in it. So that means X belongs to interior of it. Yeah. So that's the proof. Okay. Next one. Show that boundary of A is phi implies A is both open and closed. Okay. So that's actually pretty simple. So we're just going to use A part. So A closure is equal to interior of A. Disjoint union. This is one symbol. This is another symbol, and this is another symbol. So they're all the same thing. Disjoint union boundary of A, right? And boundary of A is phi, which implies A closure is equal to interior of A, and that means well, A contains interior of A equals A closure, so A is closed, and it's contained by closure of A, which is equal to interior of A. So it's contained in interior of A, which means it's open. So yeah. Now for the other direction, yeah, A closure is equal to essentially A closure disjoint union boundary of A, right? So what does that mean? That means boundary of A, if it's, so it can't, it's disjoint with closure of A, and it cannot contain anything other than the closure of A because otherwise it's not equal, right? So yeah, it's supposed to be empty. So yeah, okay. Now show that U is open if and only a boundary of U is that. Yeah. So so note that U is equal to interior of U here. We're proving in this direction, right? And yeah, so boundary of U union U is equal to U closure, right? And yeah, if we remove U from both sides, we won't be removing anything from boundary of U because they're disjoint. So yeah, we're done. Now for the other direction, let's see. Hmm. Okay, so the boundary of U is always a closed set. So that's making no difference. It would also be a closed set because, closed minus open that way. Hmm. Okay, so the boundary of U is always disjoint from the interior of U, which is equal to U. So how do we show that U is okay? We don't know anything yet. Okay. Boundary of U union U is equal to U closure, right? Okay. Hmm. Okay, so let X belong to boundary of, right? This implies that X does not belong to U essentially by this equation. Hmm. I think we're close. Let's see. So this also implies X belongs to X minus U, right? Which is closed. So any member of the boundary is going to be, yeah. Okay, U notation is a bit confusing. Hmm. Yeah, so I thought about it, and this is some proof. Well, yeah. So I'll show that U is equal to interior of U, and that's basically it, right? Yeah, that is what I have to show. Okay. So trivially, interior of U is already a subset of U, so let's show the other way. So let U not be a what? Not be contained in interior of, right? So this is only possible if there exists X. No, I'm going to choose U in U such that U does not belongs to interior of U, right? Okay. So now what? Now that means this U, since it belongs to U, it must belong to U closure, and therefore this U belongs to boundary of U, right? Since it belongs to U closure and not interior of U, and since it's a disjoint union, it must belong to boundary of U, right? Yeah. Now what? Now that means that this boundary of U is actually a strict subset of U closure minus U. Now, why is that? That's because this point that's actually in boundary of U, sorry, not strict, yeah, strict sub superset. Yeah, that's because this element that happens to be in boundary of U is actually removed, right? This U is a witness to the fact that it's a strict subset and not a, only a subset. And this directly contradicts the assumption. And that is why this is true. So that means U is open. Yeah, this took a while. But yeah, this argument is correct because we are contradicting essentially. Yeah. So if U is open, is it true that U is equal to interior of U closure? And that is false. I'll show you why. So should I take that? Yeah, okay. I was going to give an example in the metric topology again, but let's take two order topologies. So let's take 0, comma 1 and 1, comma 2, right? So its closure will be closed interval 0, comma 2, and its interior is going to be open interval 0, comma 2. Where's 1 gone? 1 is missing. So no, it's false. Yeah. Question 20. I think I'll attempt question 21 for 10-15 minutes, and then I'll just upload that as a separate video because yeah, it's supposed to be hard. I'll give it 15 minutes and then I'll stop. I'll maybe attempt it later again if I feel like it, but yeah. Okay. So I'm just going to give the answer for question 20, and it's quite intuitive. I'm not too interested in solving them. So x cross y is equal to 0. So essentially the horizontal line. So it's a closed set. How is it a closed set? Well, you just take any neighborhood. It's actually you know intersecting the complement and this. So it's actually the boundary point, and it has no interior. So the interior is the empty set and the boundary is the entire line. Yeah. Okay. For B, x is greater than 0, y is not. So let's say this is the origin. X is greater than 0, y is not equal, and not including the line. So the boundary would be, let's see, this and this, essentially this T line, essentially. And to get an idea, any point here is going to intersect the complement as well as the same set, which is given, and same thing here. Wait, yeah. So this lies in the complement actually, so it's in the boundary, and this is the set we are given. So it's intersecting both. It's the boundary point, and this point is an interior point, and an interior point is yeah. So it's essentially completely contained in the interior. So if there x is an interior point, if there exists a U contained in A such that X belongs to U in A. And this is quite similar to a basis, but instead of a basis, we're having an open set. And we can define an interior point. So yeah. Uh-huh. So this is these two, essentially the entire set itself is open and also an interior point. So why is it open? Why is it open? I'll show you. Let's see. So the interiors of the rectangles are open sets, and you can just you know, union them to get the infinitely big rectangle, and same thing onwards. So yeah, yeah. C is equal to A union D. So we're essentially joining the entire line this time. So this stops being the boundary point. This remains as the boundary, and this remains. The boundary has changed, and the interior has also changed a bit. So this becomes the interior. So boundary and interior. Okay. X is rational, D. Yeah. So this is a part of the X. No. Y is, so what happened to Y here exactly? Oh, Y is anything, huh? Okay, Y is anything that changes things a bit. I was expecting it to be a line, but it's not a line. Okay. I think every point is, okay, every point cannot be both points. So there is something. Hmm. Okay, yeah. X is rational, so, and Y is varied. So it's something like this. Except it's infinitely, it's dense, right? So between any two rationals, there's always a rational and so on, like that. But the gaps aren't filled. That's the best way of having an intuition about it. Now, you take any point here, it's going to be a boundary point because when it's intersecting, so by density of real numbers, it's going to intersect the complement as well as itself because of the density of rational numbers. So no matter what neighborhood you take for any member, it's going to be a boundary point. So the boundary is the set itself, and well, yeah, the interior is empty. Why is the interior empty? Because there is no containment. You can't find any containment. But yeah, the boundary is the set itself. So it also holds for a point set like that if you take all the rational numbers along the line in R2. Okay. E is a hyperbola, so I'll just draw it for you like that at 1 and 1. And this is the point. So this is the interior, this is the boundary. It's quite nice here. So we have the boundaries and the interior. And this is just the complement. X cross y, x is not equal to 0 and y is less than equal to 1 by x. So it's a also a hyperbola, but in that form, it's a rotated one. X is not 0 and y is less than 1 by x. Well, let's find out. In other words, hang on, is x positive? No, it may not. It can be negative, yeah, it can be negative. So essentially, we have two curves, right? And y is less than 1 by x. So if it's positive, it's here, and if it's negative, it's greater, right? Yeah. So is it this area again? I think so. Let's see. Y is positive here. Is it positive here? Yeah, it's positive here. Hang on, what even is this thing? Y is less than 1 by x. So this is 1, yeah, this is 1 by x, and y is less than that. So here. Oh, it'll be outside here too? No, it's the inside. Does it flip? No, y is negative here, right? So here, and if it's 0, it's less than, no, it's greater than minus 1 by x. Oh, it's weird. Okay. I guess so. This is included, and x is positive, 1 by x is positive. It's here, so here is any point here included. So x is here, 1 by x is here, right? Yeah, and y is not. Okay. Hmm. Okay, so yeah, let's say it's all the downward. Okay, so we'll move this and we'll move this. Yeah, that's this part and this part. Quite weird, but okay. And yeah, so the interior is interior. Okay, yeah, the boundary does extend here a bit. So this is the complement, and this is the part of it. So any neighborhood here is the boundary. This is an interior point in the complement, so it doesn't count. This is an interior point. This is also a boundary. So we have this as the boundary, this as the boundary, and this as the boundary. Anything else? I don't think so. Yeah. So the interior is this shade, and the boundary is these three lines. Okay, now let's spend 15 minutes attempting question 21 in the next video.